Good morning all. Today we are going to see the introduction about the area of computation, where we are going to study the automatas including finite automata, push-down automata and the Turing machine. And we'll start with the basic automata called finite automata. This finite automata involves states and the transition among states in response to the inputs. Finite automata is a mathematical model of the system with discrete inputs and outputs. The system can be in any one of the finite number of states, and the states summarizes the history of the past inputs and determines the behavior of the system for the subsequent input. That is, a finite automaton is an abstract model of any computational device where it consists of set of states and the transitions. So transitions for the input. At last we can able to get the output. This output can help us to identify whether the input string is accepted or not. So it receives the input as a string from an input file and it gives us output whether the input string is accepted or not. The finite automaton has a mechanism to read the input, which is a string over an alphabet. This input is actually written on an input file, which can be read as by the finite automata, but it cannot be changed by it. So this is the basic structure of the finite automata. It consists of infinite input tape, where the input tape is divided into number of cells, and it has a finite control and a control head. This control head is used to read the input symbol from the input tape, and the output is whether the string is accepted by the finite automata or not. Input file is divided into cells, each of which can hold one symbol. The automaton has a control unit which is said to be in one of the finite number of internal states. The automaton can change states in a finite way. The control head reads one symbol and moves its pointer to the next symbol. And this finite automaton is of three types: deterministic finite automaton, non-deterministic finite automaton without epsilon transition, and non-deterministic finite automaton with epsilon transition. First, we'll learn about this deterministic finite automata. In short, you can call it as DFA. So formally, we can define this DFA as a finite automaton is a quintuple, that is 5 tuple, and it is represented as M, which is equal to Q sigma del Q naught F, where this Q is finite set of states, sigma is finite set of input symbols or is alphabet, set of alphabets, and del is the transition function which may maps a state with the input symbols and returns any state, and Q naught is a initial state which belongs to set of states, and F is subset of states which is final subset of states, which is said to be final state or acceptance state. The deterministic finite automata can be represented by both a transition diagram and also transition table. First, we'll learn what is transition diagram. A DFA can be represented by the transition diagram as a directed digraph. The steps for constructing the transition diagrams are as follows. The vertices, that is the nodes in the transition diagram, are the states of the finite automata. The edges represents the transitions. If there is any transition from a state Q1 to Q2 on an input symbol A, then draw an edge from Q1 to Q2 labeled A. The initial state should be indicated by the arrow in front. You may have a label called start, and the final state will be indicated by the double circle. So in order to differentiate the final state from all other state, we are going to use a double circle to represent the final state. And the next representation is transition table. A transition table is a conventional tabular representation of a function like del, the transition function, that takes two arguments and return a value. A rows of table correspond to the states and the column of the table correspond to the inputs. The entry for the row corresponding to the state Q and the column corresponding to the input A is the state. That is del of Q comma A is P. So Q is the current state, A is the current input symbol, P is going to be the next state. So this is how the transition table will look like. So now we'll see one example. So consider a deterministic finite automata accepting all strings with a substring 0, 1. So here first we'll identify the set of strings accepted by this finite automata. So 0, 1 is a primitive string which can be accepted by this finite automata. And then so here we can able to get that 0, 1 is a substring. So if so, 0, 1 is the primitive string, 0, 0, 1 and 0, 1, 1 is the next set of strings that are with the length 3 is accepted. Then we'll go for length 4, string with length 4. That is you can take 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. So these are all the uh, four strings of length 4 and which has the substring 0, 1 and which are accepted by this DFA. And this is actually a transition diagram. So from the state Q naught, so Q naught is the initial state. So here it starts with an arrow mark labeled start. And for 0, so from the state Q naught, if we read 0, the machine goes to Q2 state. And from Q2, when we read 1, it goes to Q1. Or else from Q naught, when we read 1, it stays in the same state. And for 0, it goes to Q2. And for 0, again it stays in the same state. Then for 1, it goes to the final state Q1. So when it reaches the final state, afterwards it can read any number of zeros and ones. So that we can draw a self loop where you can give an input symbol as 0 and 1. So this is the transition diagram for the DFA accepting all strings with the substring 0, 1. The specification of the DFA accepts the language L of the string that have 0, 1 as a substring. So we know the FA can be represented with the 5 tuples. So M is equal to set of states Q. So what are the set of states here? There are 3 states, Q0, Q1, Q2. And set of input symbols. So there are 2 input symbols, 0 and 1. And set of transition functions. So del and Q0. Q0 is the initial state. Q1 is the final state. Where this del can be a transition function and which can be represented as a table also. That is transition table. So here rows represents the states and column represents the input symbols. So for Q0, 0, Q2, Q0, 1, Q0, Q1, 0, Q1, Q1, 1, Q1, Q2, 0, Q2, Q2, 1, Q1. So this is called as the function representation. Del of Q0, 0 is equal to Q2, del of Q0, 1 is equal to Q0, del of Q1, 0 is equal to Q1, del of Q1, 1 is equal to Q1, del of Q2, 0 is equal to Q2, and del of Q2, 0 is equal to Q1. So this is the transition table representation. Next we'll see another example. Design a deterministic finite automata to accept the language L is equal to set of string W such that W is of even length and begins with 0, 1. So here we're going to design a deterministic finite automata where the set of strings of even length, and also we have another condition that it should begin with 0, 1. So 0, 1 is a string which begins with 0, 1 and whose length is also even. So this is going to be the primitive string and which can be accepted by the DFA. Afterwards, you can have any string 0, 1, 0, 0. So here begins with 0, 1 and whose length is 4. So it is even length. And then 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. So these are all the string with length 4, even length, and which starts with 0, 1. So, set of all strings which begins with 0, 1 and whose length is even should be accepted by the DFA, which we are going to draw. And then we are asked to check whether the string 0, 1, 1, 1, 0, 1 is accepted or not. Yes, this has to be accepted because it begins with 0, 1 and whose length is 6, so it is in even. Okay, for that first you have to construct or design a deterministic finite automata. Okay, we know that the primitive string is 0, 1. So in order to accept 0, 1, so you can draw a transition diagram from Q0 to Q1 for 0 and Q1 to 1 for 1. Okay, so begins with 0, 1. Afterwards, you should have the even length. So in order to accept the string which are in even length, so from Q2 to Q3, you can read any number of zeros and 1, and Q3 to Q2, you can read any number of 0, 1. So this is for the even length string. So this is the uh, DFA which can accept the string which begins with 0, 1 and whose length is even. So here the number of states are 4. So Q is equal to Q0, Q1, Q2, Q3. And what is the initial state? Q0 is the initial state. And what is the final state? Q2 is the final state. So here final state is represented with a double circle. And what is sigma? Sigma is equal to 0, 1. The input alphabet 0, 1, 1. So we can have the 5 tuple representation. So Q0 is the initial state. Q1 is the state entered on reading a 0 from Q0. And Q2 is a state entered on reading 0, 1 initially, because we have to accept the string which begins with 0, 1 alone. So automaton subsequently returns to this state whenever the substring seen so far starts with 0, 1 and it is of even length. And here you have a state Q3. The DFA enters this state whenever the substring seen so far starts with 0, 1 and is of odd length. So look at here, this Q3, the machine can land at this Q3 after reading 0, 1 at the beginning and afterwards a even length of string. And Q2 starting with 0, 1 and reading even length string. So this Q2 becomes the final state. Okay, or else you can also include a dummy state or the dead state Q4. Okay, because at this state Q0, you may read 1. So when the machine reads 1, where should it go? In order to represent that, you may include a dummy state or a dead state. Here, this Q4 is a dummy state or the dead state. From state Q0, suppose the string starts with 1, it can enter into Q4. Afterwards, it may read any number of zeros and ones. Okay, and also whenever in Q1, the next symbol is to be 1. Suppose if we are reading 0, we can go to this dummy state or the dead state. Okay, where this Q4 is a state which is called dead state or empty state. So this state is entered whenever a 1 is encountered in state Q0 or a 0 is encountered in state Q1. Okay, next what we have to do? We have to check the string 0, 1, 1, 1, 0, 1 is accepted or not. Okay, we'll check. First from the state Q0, for the 0, the machine goes to Q1. Then from Q1, for 1, it goes to Q2. From Q2, for 1, it goes to Q3. Then from Q3, for 1, it goes to Q2. Then from Q2, for 0, it goes to Q3. Then Q3, for 1, Q2. So after reading the entire string 0, 1, 1, 1, 0, the machine lands at Q2, and Q2 is the final state or the accepting state, so that we can say the string is accepted. Okay, next we'll see the extended transition function of a DFA. So we know del is a transition function. Then what is this extended transition function? If del is our transition function, then the extended transition function constructed from the del will be called del cap, or else you can use del dash. We define this del cap by a induction on the length of the input string as follows. At the base step, we can take the empty string. So whenever you are in state Q and we didn't read anything, you will be in the same state, isn't it? In DFA. So if we are in the state Q and read no input, that is empty string, then we are still in the state Q2. Q. Then in the induction step, we are taking a string whose uh, just W. Okay. So in general, you can represent a string with a W. So del cap of Q comma W can be represented as del cap of Q comma X comma A. That is, you can substitute this W as XA. Okay, a some substring X and which ends with A. So how can you identify? So for the substring, you have to identify the transition. At last, you can find for the last symbol A. Suppose the W is a string of the form XA. A is the last symbol of W and X is the string consists of all but not the last. So next problem. Design a deterministic finite automata to accept the language L is equal to set of string W such that W has both an even number of zeros and even number of ones, and illustrate the transition function del, and we have to use a W given like 110101, and we have to check whether it is accepted or not. So this is a finite automata which can accept a strings of even length where you can have even number of zeros and even number of ones. So look at here. So Q0 is the initial state. So for when we take 0, 0. So for the 0 it goes to Q3, and again for the next 0 it goes to Q0. Similarly 1, 1. So these two are the very basic primitive strings. And also we can consider here epsilon. So from Q0, epsilon. So 0, you may consider 0 as a even length so that it may accept epsilon also. And suppose if you are having 4 zeros, so 40 is also accepted, 41 is also accepted, and 0101 is accepted or not. 0101 is accepted. 0011 is accepted. So all the strings whose length is even and it has even length of zeros and ones is accepted by this finite automata. So then we'll define it. L is equal to D of A should count both number of zeros and a number of ones. So here you have a states Q0, Q1, Q2, Q3, where Q0 both the number of zeros seen so far and the number of ones so far are even. This is a start state and accepting state. And what is this Q1? The number of zeros seen so far is even, but the number of ones seen so far is odd. What is this Q2? Both the number of zeros seen so far is and the number of ones seen so far are odd. What is this Q3? The number of zeros seen so far is odd, but the number of ones seen so far is even. So look at here. So number of ones seen is even, 0 is also even. What is this Q1? Number of ones seen is odd, but number of zeros is even. So here, what is this Q2? Number of ones and zeros seen as odd. What is this Q3? Number of zeros seen as odd, but number of ones seen is even. So this is a place where you can see both the number of zeros and ones as even. So this is a finite automata which can accept number of zeros and ones are even length. In the corresponding transition table, there are 4 states Q0, Q1, Q2, Q3, and this Q0 is the initial state as well as the final state. So in the transition diagram, you can use double circle to differentiate the final state from other state. But in table, you have to use a star to indicate a state as the final state, arrow mark for starting state. So Q0, 0 is Q3, Q0, 1 is Q1, Q1, 0 is Q2, Q1, 1 is Q0, Q2, 0 is Q1, Q2, 1 is Q3, Q3, 0 is Q0, Q3, 1 is Q2. So now we'll check whether the string 110101 is accepted or not. So here we are going to use a extended transition function. So we have to start from the basis step. So basis step, we'll be taking the null string. So from Q0, if we didn't read anything, you will be in the same state. So Q0 comma epsilon is Q0. Then you have to take the 1. So from this Q0 you have to take this one. So from Q0 for 1, so Q0 1 Q1. Again the next 1 1. So for that 1 1, how can you identify? So first you have to take for the first one, next to 1, next. So Q0 1 is Q1. From the previous step you can get. Okay, from that Q1 you have to identify for 1. So Q1 comma 1 is Q0. So how will you do for this 1 1 0? So first you have to find for 1 1, then for 0, and from 1 1 we have get from the previous. So after this 1 1 you are at Q0, and from Q0 for 0 Q3. Then how can you identify for 1 1 0 1? So first you have to take the transition for 1 1 0 from the previous step. So where we are in 1 1 0, we are at Q3. So after Q3 you have to check for the 1. So Q3 comma 1 is Q2. Listen. Next, then for 11010, so we have to take the previous step, that is 1101 as Q2, and for 0 you have to find out the transition which is Q1. Again 110101. So for here the previous step we have gone through for 110101 to Q1. So from Q1 to 1, this is Q0. We know that Q0 is a final state or the accepting state, so that you can conclude the string 110101 is accepted. Okay, from here we can able to define what is the language accepted by the DFA. So we can define the language of DFA is equal to Q sigma del Q naught F. This is the language denoted by L of A and defined as L of A is equal to W such that del cap of Q naught comma W is in F. That is, set of string W starting from Q naught. After reading a W, the string sequence of input symbols, if you are in the state F, any one of the state in F, then you can call the string as accepted. So which is nothing but the language of the DFA. That is, the language of a finite automata is set of strings W that takes the start state Q naught to one of the accepting state. So that's all about the deterministic finite automata. Next we'll learn about non-deterministic finite automata. A non-deterministic finite automata, in short you can call NFA, has the power to be in several states at once. So the definition, again it consists of 5 tuples Q, sigma, del, Q naught, F, where this Q is finite set of states, sigma is finite set of input symbols, Q naught is initial state, F is set of final state or the accepting state. But here this Q is a transition function which maps the states with the input string to the powers of set Q. So Q comma sigma tends to 2 per Q. So for the input symbol, there may be 0 or more transition. So here is the difference between the non-deterministic finite automata and the deterministic finite automata. In deterministic finite automata, there should be only one next state, whereas in non-deterministic finite automata, 0 or more next states are possible. We'll see one example for that. So look at here, you have 3 states Q0, Q1, Q2, and from this Q0, after reading 1, the machine may enter into Q1 or it can stay in the state Q0. So there are two possibilities for reading 1 from Q0. So this is called non-determinism. So it can be specified as with a 5 tuple representation. There are 3 states Q0, Q1, Q2 and the two input symbols 0 and 1, and del is the transition function, Q0 is the initial state, Q2 is the final state. And how can you write the transition function? So transition function can be written with the help of transition table. So Q0, Q1, Q2, Q0 is the initial state, Q2 is the final state for 0 and 1. So q naught comma 0 is q naught comma 1. There are two states, so set of states q naught comma q1. q1 comma 0 is q2, q1 comma 1 is also q2, but q2 comma 0 is pi, q2 comma 1 is pi. So here some of the transition is not yet mentioned. So 0 or more transitions. So here you can find 0 transition. So since it is pi, here you can say you can find one transition, that is q naught comma 0 exactly goes to q naught. But for 1, there are two possibilities of transition, that is q naught and q1. So there exists a non-determinism here. Then we'll learn the extended transition function for this NFA. So here also we can use del cap in order to represent the extended transition function of an NFA. So in the basis step q naught comma epsilon. So when you are in state q1, when we read nothing, so we'll be in the same state. That is without reading any input symbol, we are only in the state v beginning. So induction state. Suppose w is of the form w is equal to xa. Then a is the final symbol w and x is the rest of this w. Also suppose that del cap of q comma x is some set of states q1, q2, p1, p2 and so on pk. Then we can get a transition for a by taking the union of all the states. So union I is equal to 1 to k del of pi comma a. It is going to return some set of states which is going to be r1, r2 and so on rm. So at last what you can able to conclude, this del cap of q comma w is equal to some set of states r1, r2 and so on rm. So describe how the string 0, 1, 0, 1, 0 is processed by the previous NFA that we have designed. So as from the definition for the basis step, del cap of q naught comma epsilon is q naught. Okay. Then del cap of q naught comma 0 is, the previous step answer is q naught, and for 0 you have to find out. So q naught comma 0 we know q naught. Then q naught comma 0 1. So for which we have to get the answer from the previous step. So which is nothing but q naught comma 1. So q naught comma 1 is, there are two states q naught q1. And for 0 1 0 we can get the answer for 0 1 from the previous step, which is nothing but q naught q1. But we have to take the union. So q naught comma 0 union q1 comma 0. So q naught comma 0 is q naught, q1 comma 0 is q2. So that the answer is q naught q2. So after reading this 0 1 2 1 0, there are two possibility of existence, that q naught comma q2. And then q naught comma 0 1 0 1. So from the previous state we can get two states, that q naught q2, and for which you have to find for 1. So q naught comma 1 union q2 comma 1, which is nothing but q naught q1 union pi. At the last you can get q naught q1. And for the last symbol 0, you have to get q naught comma 0 union q1 comma 0. So q naught comma 0 is q naught, then q1 comma 0 is q2. When you take union, you will get q naught q2. So here in this set, we have the final state q2. So if the suppose the set contains the final state, then we can say the string is accepted. So that how can you define the language of NFA? If any machine or automaton is equal to q sigma del q naught f, then this L of A, the language accepted by the A, is equal to set of string W such that q del cap of q naught comma W intersection F is not equal to 5. That is, you will be resulting with some set of states. Then you have to take intersection with the final state. So from the previous problem, Q2 is the final state. When we take Q naught q2 intersection q2, we will be getting q2. So if it is not equal to pi, then we can say yes, here we are getting q2, isn't it, which is not equal to pi. Then what we have, we have concluded it is accepted, isn't it? So here also when will you say the language is accepted? So after processing the string w, when you are landing at any one of the final state, then you can say the string is accepted. So del cap of q naught comma w contains at least one accepting state. So next we will compare this NFA and DFA. So the automaton in which for any input symbol from a given state, those are many possible transitions. There are many possible in non-deterministic finite automata, but in DFA there exists only one transition. In this diagram itself you can see from 1 for a there are two possible transition, and from 2 For B, there are two possible transition, but here for which and every input symbol there exists only one transition. So here this is the major difference between NFA and DFA. Then you can say it maps Q cross sigma is equal to 2 pi k because more than one transitions are possible here, but here only one next state exists. Okay, and what about the time complexity? The time needed for the executing an input string is more because you may have more than one path. All the paths you have to process in order to conclude. But here the time is very less because you'll be having only one path. So all NFAs are DFAs, but all DFAs are not NFAs. The languages of NFA. So if A is equal to the 5 tuples Q sigma del Q naught F is an NFA, then L of A is equal to set of string W such that del cap of Q naught comma W intersection F is not equal to pi. But here you can say it belongs to F. So these are all the differences between NRFA and DRFA. So next we'll see construct DRFAs and NRFAs accepting the following strings over the alphabet 0, 1. So how can you construct NRFA? So NRFA is very easy to construct. So here you are given with some problem. The set of all strings begin with 101. So 101. So it should begin with 101. Afterwards you can have any strings of zeros and ones. So at the beginning 101. So for 1 from Q0 to Q1, for 0 from Q1 to Q2, and for 1 Q2 to Q3. And whenever in Q3 after reading this 101, you can read any binary string. So any binary string can be represented with a self loop having 0, 1. Same thing is going to be the NFA because here you can see there is no more states for any of the input. We have only one set of next state. So that's what all the DFA is NFA, but not all NFA is not DFA. The set of all strings containing 1101 as a substring. Okay, first you have to identify the primitive string. So primitive string is 1101. So 1101, you have to give 4 states starting from Q0 to Q4. Okay, then already you have drawn for 1. Next you have to check after reading 0. So the substring is 110. So beginning it may read any 0. So 0 self loop. Then come to this Q1. So already you have defined the transition for 1. Now you have to think about 0. So when you come to here this Q1 after reading 1. So after reading 1, so this path goes to this Q4. So it can be in Q4 only when it read 1101. So that what you can do, you can go to this state Q0 state. Clear? Then from Q2. So Q2 for 0 already you have defined. Suppose if you are reading 1, what happens? So you know that 1101 is a substring. So previously you have read 1 so that you are in state Q2. It is enough to read 1 again. So go to this Q1 and then Q3. So Q3 1 is already defined. Now you have to define for 0. So from the state Q3, if you are reading 0 in the sense, go to the state Q0 because only when you read 1101 as a substring, you can reach to this Q4. So just redirecting the state to Q4. After reading the 1101 as a substring, the machine can halt at Q4. So when you are in Q4, so after reading this 1101 alone, you can be in Q4. So afterwards, you can read any strings of zeros and ones. So how can you represent any strings of zeros and self loop 0, 1. Next, the set of all strings with exactly 3 consecutive zeros. So in between, you should have 3 consecutive zero. At the beginning and the end, you may have any number of ones. So exactly 3 consecutive zeros. More than that will not be accepted. So 3 zeros continuously you have to process at the beginning, at the end. You may have any number of ones. Next, set of all strings which contains 3 consecutive zeros, but here exactly 3 consecutive zeros is not given. So that you may have any number of ones in between also, but 3 consecutive zeros should be there to reach to the final state. So here you can introduce a transition for 1 also. Next, construct DFA for all the set ending with 0, 1. So 0, 1, okay. Primitive string is 0, 1. Then when you are in Q naught, when you read 1, so ends with 0, 1. So beginning it should, you may have 1, no issues. So self loop. Then at Q1, when will you be in the Q1 after reading 0? So again, you know that you can reach to this final state only when you read 0, 1. So go to Q naught. Next, list of all strings containing 1101 as substring. So we know that in between you should have 1101. At the beginning, at the end, you may have any number of zeros and ones. So here we are drawing NFA. So we won't bother about undefined states here. For example, for Q1, for 0, what is the transition? We don't know. It's fine. Q2, for 0 is already defined. For 1, we don't know. It is not undefined. No issues. So at the middle, 1101, at the beginning and the end, you should have any strings of zeros and ones. That's it. Some of the states are undefined. No issues. And here also for the state Q naught, for the input symbol 1, there are 2 transitions possible. No issues. So designing NFA is easiest than designing DFA. So set off all strings which exactly 3 consecutive 0. No issues. So we can have ones in the beginning, at the end, in between you may have 3 consecutives. So the same thing you can use for next problem, but here you can include zeros here because not exactly 3 zeros. You can have 0 or 3 or more zeros. So that at the beginning and the end you can have this 0, 1. Then construct NFA for all set of strings ending with 0, 1. So here it ends with 0, 1. Beginning you may have any number of zeros and 1. So Q naught, 0, there are 2 possibilities. You may be in Q naught or you can go to Q1. This is called non-deterministic finite automata. Then give the DFAs accepting following string over 0, 1. So set off all strings such that the number of ones is even and number of 0 is multiples of 3. There are 2 conditions given. What is the first condition? The number of ones is even. So even number of ones. So 1. So Q3, Q1. Q3, Q naught. So this can handle even number of ones. And the number of zeros are multiples of 3. Multiples of 3. So adding one more state Q1 and again you can have Q2. So multiples of 3, 3 zeros. So first 3 zeros, after reading 3 zeros, you can go to this Q naught, isn't it? Then 6 zeros you can go to. So both the things are handled here. Okay. And we know that whenever it is DFA, you have to define for zeros and ones. So already here you have defined for 1. So if you are reading 0, so where should you go? So you can go here. So you have defined for 1 and 0, so no issues. So for each and every state, for each and every input symbol, you have to define the transition whenever you go with the deterministic finite automata. Next very important problem, set of all strings not containing 110, not containing. So how can you draw not containing? Very simple. First you have to draw for containing 110, then you have to convert the final state into non-final state. So when you draw DFA which accepts a string containing 110, this Q3 will be the final state. So that what you can do, you can convert this final state into non-final state and all other state into final state. So that you can mark this Q3 as a single state and this Q0, Q1, Q2 as a double circle. So here this is the finite automata which can able to accept the string which is not containing the substring as 110. Next, set of all strings that begins with 0, 1 and ends with 1, 1. So begins with 0, 1 and ends with 1, 1. But this is going to be the DFA. So that what you have to do, you have to concentrate on all other possibilities of input symbol. Next, construct DFA to accept the even length of ones. So even length ones. So 2 ones, 4 ones, 6 ones, 8 ones. So this is the diagram. Next, construct a DFA to accept the string over 0, comma 1 such that the number of ones in a string is 3 mod 4. Okay, so mod 3 mod 4. So what is 3 mod 4? 3 mod 4. So modulo is a division. So which is nothing but 3. The number of, so whatever may be the input given, the number of ones should be 3 mod 4. In the sense, it should be 3. 3 mod 4 value was 3. So look at here. So it can accept only 3 ones. Next. Design a DFA to accept this string over sigma is equal to 0, comma 1 with 2 consecutive zeros. 2 consecutive zeros. So two continuous 0 you should have. Otherwise it should not accept. So two zeros. Or else it will not accept. Design a DFA which checks whether the given unary number is divisible by 3. So you have to find out the number of ones. So 3 ones accepted. Again 6 ones accepted. 9 ones accepted. 12 ones accepted. Okay, this is the DFA. Next, set of all strings do not end with 0, 1. Do not. First what you have to do, you have to construct a machine which can accept the string which ends with 0, 1. Then you have to convert the final state to the non-final state and non-final state to the final state. That's it. Next, construct an NFA that ends with a string 1, 1 for set of all strings 0, comma 1. So here ends with set of all strings 0, comma 1. So 1, 1 ends with 0, 1. Okay, at the beginning you may have 0, comma 1. So here we have drawn a NFA. Then construct NFA for set of all strings 0, comma 1 that ends with 3 consecutive ones at its end. 3 consecutive ones at the end. At the beginning it may have any number of zeros and ones. Next, construct NFA for set of all strings 0, comma 1 with 0, 1, 1 as substring. 0, 1 as a substring. At the beginning, at the end, it may have any strings. Next, give non-deterministic finite automata to accept the following over 0, comma 1. Set of all strings such that containing either 110 or 101 or 110 as a substring. So here, in the both the thing, the first first symbol is 1. So afterwards, in one thing 0, 1, in another thing 1, 0. So this is the diagram. Okay, or else you can draw like this also. So here you can reduce the number of states. Then set of all strings of zeros and ones whose number of 0 is divisible by 5. So previously we have seen divisible by 3, here divisible by 5. So primitive string is 5 zeros, then 10 zeros, then so like that it goes. Next. So very important, equivalence of NFA and DFA. The strings which are accepted by NFA is also accepted by DFA. The theorem statement is given like, let L be a set accepted by NFA, then there exists a DFA that accepts L. We know that L is a language. Okay, suppose the language is accepted by any NFA, then the same L is also be accepted by a DFA. Okay, so how can you say this is the language accepted by NFA is also accepted by DFA? Only when you have a equivalent of NFA and DFA. When you can convert NFA to DFA, then the language accepted by the NFA is also accepted by the DFA. Okay, I will see a proof. To prove, both NFA and DFA are accepting the same string belongs to the language L. Okay, so NFA with the N, DFA with the D. So 5 tuples of NFA, Qn, sigma, del n, Q naught, Fn. 5 tuples of DFA, Qd, sigma, del d, Q naught, Fd. Actually, we prove del d, Q naught, comma W is equal to del m. The language accepted by is DFA is nothing but the language accepted by the NFA. So in the basis step, what you are going to take? A string W whose length is 0. Okay, so string whose length is 0 is nothing but the epsilon. So in DFA, we know del Q naught comma epsilon is equal to Q naught. And NFA also Q naught comma epsilon is Q naught. So here both the states are equal. So that you can say This is accepted. So we are going for the induction state. Let W be the length of n plus 1. Okay, first assume that the statement for the length n is true. So we can break the W into xa, and we can say this x is of length n and a is 1, isn't it? So that del d of q naught comma x is equal to del n of q naught comma x. So for a, how can you identify? So we know that in n of a, we'll be having some set of states. So del d of q naught comma w is equal to del d of qd q naught comma x comma a, and this q naught comma x comma a is p1, p2, pk, from where you have to find for a, and that will result with some states. Okay, so that what you can able to conclude here, the set of states are going to be the single state for the T of A. So L of D is equal to L of N. So we using this, we'll convert N of A to D of A. So there are three states. Q1 or 1, 2, 3 are the three states. 1 is the initial state and 3 is the final state, and A comma B is the sigma. So this is given. So first what you have to take, so del of A comma A, that is del of 1 comma A is equal to 1 comma 2. So first you have to take the initial state as A. Okay, for that initial state you have to find the transition for the input symbol A and B. Okay, and for A you are going to 1 comma 2. So you can rename it as B. And this A comma B is 1. So already we have defined the 1 as A. Next, you have to find the transition for the new state. So what is the new state we have arrived so far? 1 comma 2. Okay, so that is nothing but D. Okay, and this B comma A, again it goes to B. Again B comma B, we are getting a new state 1 comma 3, and you can rename it as C. And again for the C, for A you have to find out which is equal to B. It is already existing. And B comma C. B comma C is a already existing state which is equal to A. So what the last you can able to conclude, new states are A, B, C, and for the state A and for input symbol A, we are going to the state B, and for the state A, for B, A, B comma A, B, B comma B, C, C comma A, B, and C comma B, A. So this is the final DFA. So whatever given in the NFA is now converted to a DFA. In the next problem, construct D of A equivalent to the N of A. M is equal to, there are four states given, P, comma, Q, comma, R, comma, S. Then 0, 1 is the input symbol. Del is the transition function which is given in the table. Next, P is the initial state. In Q, comma, there are two final states. Okay. So this is the transition function. So all those things you have to solve at your home as a homework. Next, we have equivalence of N of A with epsilon transition and N of A without epsilon transition. So now we are going to learn N of A with epsilon transition. So N of A with epsilon transition is going to have a 5 tuples Q, sigma, del, Q naught, F as usual, and similar to D of A and N of A that we have seen so far. But there are some difference with the del that we'll see now. Where Q is a set of states, sigma is set of input symbol, Q naught is the initial state, F is set of accepting state, and del is a state mapping function which maps a state with the input symbol, either the input symbol or the epsilon. So here there is going to be a transition for the empty string also, that is without reading anything also the machine can make a move from one state to another. Okay, and returns to per Q. So 0 or more number of next states are possible. That is the property of the NFA. So NFA with epsilon transition, as the name itself you can able to understand, there is a transition possible for without reading any input string, that is for epsilon. Okay, then we'll go for this extended transition function of. So extended transition function, as usual you can know that del cap. Okay, in the basic step, that is for epsilon. So this epsilon, when you make a transition for epsilon, which is nothing but you can define as e-closure. Okay, so first we have to know what is e-closure. So e-closure of Q can be a state Q by following all transition out of Q that are labeled epsilon. So from the state Q1 for reading epsilon, so from state Q1 we can go to 2, 3, 4 and also 5. So e-closure of 1 is 2, 1, 2, 3, 4, 5. Then e-closure of 2. E-closure of 2 is 2, 3, 4, 5. E-closure of 3, 3, 4. E-closure of 4. So when we are in state 4, when you read nothing, So there is no explicit transition given for the epsilon. So where will you be there? You will be in the same state. That is what you have to write it as 4. Eclosure of 5 is 5. You cannot write pi. Okay. So for that also we have algorithm or the theorem. Language L is accepted by some n of a with epsilon transition if and only if L is accepted by n of a. That is equivalence of n of a and E n of a. E n of a is nothing but n of a with epsilon transition. So you are given, that is, let us assume a given n of a with epsilon transition ne and n of a n. Okay, and some final state you have, and del nq comma a is equal to del neq comma a. Both are equivalent. So here you have to prove if L is accepted by E n of a and it is also accepted by n. So in the basis step we can check with A. Then what you can do, you can have assumption. Assume the string y length k is accepted by the n of a n, that is also accepted by n of e. Then del n cap q naught comma y is something which is from del ne, that is n of a with epsilon q naught comma y. Okay, so that what you can able to prove. At last you can take the eclosure and you can find the transition and both becomes equal. So now we will see one problem. How to convert en of a to n of a. So here the en of a given is, there are three states q0, q1, q2 and some transitions. Okay, first what you have to do, you have to take a eclosure. So eclosure of q0 is q0, q1, q2. Eclosure of q1 is q1, q2. Eclosure of q2 is q2. Okay, then we have to process the states. So q0 comma 0. How can you identify q0 comma 0? First you have to check the transition for q0 for epsilon. Then you have to take for 0. Then you have to find out for eclosure of the resultant answer. So that what you can able to conclude. So q0, q1, q2. So from the state 0, from the state q0, after reading 0, you may be at q0 or at q1 or at q2. So look at this diagram. When you read 0, you can be in q0 or else you can go to q1, because there is a possibility of going from q0 to q1 without reading anything. So when you read 0, you can be in q0 or you can go to q1 or you can go to q2. That is what the answer we have got here. And q0 comma 1. So when you are in state q0 without reading anything, you can come here. After reading 1, you can go to here. So that is what q0 comma q1 is q1 q2, and q0 comma q2 is q2, because without reading anything you can go to the states and you can reach through this q2 after reading this 2, isn't it? Then processing the state q1. So from q1, what are the states for 0, 1, 2? Okay, so q1 comma 0 is pi. So look at here. So q1 comma 0, you can go to q2 without reading anything, but after reading the 0 you cannot move further, isn't it? So q1 comma 0 becomes pi. Similarly q1 comma 1 is q0 q1. Then q1 comma q2 is q2. Then you have to process this last state q2. So q2 comma 0 is pi, q2 comma 1 is pi, and q2 comma 2 is q2. Clear? So another problem here you have given with 3 states and 3 input symbol A, B, C. Okay, so solve this as homework. So first you have to take the eclosure for all states. Then you have to take each and every individual states and you have to find the transition for all possible input string. First you have to take P and A, P and B, P and C. Then the next state Q comma A, Q comma B and Q comma C. Then R comma A, R comma B, R comma C. So at last this is going to be the answer. Clear? So there are more problem given. You take it as a homework and solve. Okay, next. Since we can able to convert n of a with the epsilon transition to n of a without a epsilon transition, we know that n of a's are converted to d of a. So that what you can do, you can convert n of a with the epsilon transition to d of a. So how to convert n of a with epsilon transition to d of a now? Okay. First, you have to take E-closure for all states. Okay, then you have to identify the initial state of DFA. So initial state of DFA is in E-closure of the initial state of ENFA. So here initial state is going to be Q0, Q1, Q2. And for that state A, for the 0 you have to find out. So first what you have to do, you have to take the E-closure. Okay, so already we have taken E-closure, which is nothing but Q1, Q0, Q1, Q2. So from where you have to find the transition for 0. At last you have to take the E-closure. So again this A comma 0 becomes A, and A comma 1, then A comma 2. So here wherever you get a new state, for that new state also you have to find a transition. So here you have got B as the new state, and for that B, the transition for 0, 1, so all other possible input symbols. So that is 0, 1, 2. Okay, and so for 0, B comma 0 is pi, B comma 1 is Q1, Q2, and B comma 2 is Q2. And we know that we have got a new state C, and for that C, 0, 1, 2. And C comma 0 is pi, C comma 1 is pi, and C comma 2 is C. So that, look at here, there exists only one transition for each one, and there is no epsilon transition. Clear? So everybody clear about it? Okay. Shall we revise it? So first we have learned finite automata. So what is a finite automata? So finite automata is abstract model of any device. It consists of infinite input tape, where the tape is divided into number of cells, and each cell can hold one symbol at a time. And it has a finite control, and the finite control has a read head, and the read head is used to read the input symbol, okay, from the input tape, and it can decide on the string which we have given. So it can check whether it is accepted or not. So how can you say it is accepted or not? After reading the input string, when the machine can hold at the final state, then we can conclude the string is accepted, otherwise it is not accepted. And there are three types of finite automata. What are they? A deterministic finite automata, non-deterministic finite automata, and non-deterministic finite automata with epsilon transition. Clear? And how can you represent the finite automata in general? There are two representations: transition diagram and transition table. So transition diagram is directed graph representation. Tabular representation is transition table. Okay, so in general, finite automata consists of 5 tuples, whatever it may be. Deterministic finite automata or non-deterministic finite automata, there are 5 tuples. Okay, so what are the 5 tuple? Q, sigma, del, Q naught, F. So Q is finite set of states. Sigma is finite set of input symbols. Del is finite set of transition functions. So Q naught is the initial state, and capital F is finite set of final states. Set of final state meaning more than one final states are possible. Okay, so how can you differentiate DFA, NFA, and ENFA? So in DFA, from a state for an input symbol, there will be only one next state, whereas in NFA, there are 0 or more next state. But in ENFA, there are more than 0 or more next state, and also you can make a transition for epsilon. So here is the difference between all those things. And we know that when you are given with the NFA, we can convert it to a DFA. And you are given with the NFA with epsilon transition, we can able to convert it to a NFA without epsilon transition, and also DFA. Okay, that's all about a finite automata and its equivalence among the types of finite automata. I think you people understood about the finite automata clearly. In the next class, we'll learn about regular expressions and the regular languages. So languages that are accepted by the finite automata are called as regular languages, and which can be represented with a simple expression called regular expression. So in the next class, we'll learn the regular expressions and the regular languages. Thank you, students.